Okay, welcome to Chapter 11, the last chapter in our book. We'll be talking about chi-squared distributions. So 11.1, we're asking a question about two categorical variables. A categorical variable is something like, in our first example, gender and class. We ask the question, are they independent or are they somehow related? And if they're independent, we know that there cannot be any causal relationship. In other words, one doesn't cause the other. For a chi-squared test for independence, we first state the hypotheses and the level of significance. The null hypothesis is that the two variables are independent, and the alternative hypothesis is that the two variables are in some way dependent. Our assumptions are that we've got a random sample and that we've got at least 5 of all of our observations. The test statistic and the p-value come in step 3. The test statistic is chi-squared, and it is used to calculate our p-value. As always, if the p-value is less than alpha, we reject the null hypothesis in favor of the alternative, and we say that there is sufficient evidence to support the alternative hypothesis. That is, the categorical variables are dependent. Otherwise, we say there's not enough evidence to support the alternative hypothesis. The interpretation is when we state what the conclusion means in the context of the problem. The test statistic is chi-squared. Chi-squared is a single number that captures the most important part of independence. It asks how far is the observed data away from what we'd expect if the null hypothesis is true. Now, to do this, we just take the sum of the squares of the differences, but then we have to divide out the units, that is, normalize it to make a unitless number. Here are two categorical variables for the survivors of the Titanic. The first is gender and the second is class. So the two genders are male and female, the three classes are first, second, and third. And these are actually the observed counts. The number of women in first class who survived, for example, is 134. The number of third class passengers who were male who survived was 58. And then along the bottom row and the far right column, you can see the totals. That 450 tells us that 450 people survived the Titanic. The next part of the question is to say, what would we expect if the null hypothesis is true? That is, if class does not affect the proportion of women who survive and gender does not affect the proportion of each class who survive. So basically we start with the table with the observed numbers taken out, but the totals still there. So in other words, we still expect of the 450 passengers who survived, we expect 308 of them to be women. Similarly, of the 450 passengers who survived, we expect 193 of them to be first class. So let's ask this question for one cell at a time. What would we expect if gender is independent of class? So let's look at the third class female cell. So when we look at it, that's right down here, we can ask the question, among the 450 survivors, 308 were women. So that's 68.4% approximately. So if there was no relationship between gender and class, then that same percentage of third-class survivors would be expected to be women. In other words, of the 138 third-class survivors, would expect 68.4% of them to be women. That's 94.45. Now, we can work out this number the same way by asking a different question. Among the 450 survivors, 138 were from third class. That's 30.7%. Again, if there were no relationship between gender and class, that same percentage of female survivors would be expected to be from third class. 30.7 of the 308 female survivors is again 94.45. If you think about that for a little bit, you can see that the proportion has to be the same whether we're considering that gender is independent of class or class is independent of gender, which means that we have an excellent, relatively straightforward formula to compute the expected count if, in fact, the two categorical variables are indeed independent. So when we go through and do that, here's our 94.4. That's the number of third-class women we would expect to survive. We do that for all the numbers in the table, and now we ask a question. And our question is, how far apart are these two tables? Now we're going to use the word matrices now. Matrices is an algebraic word. It basically is an array of numbers. It's also a feature in our calculator. So by using the correct mathematical notation matrix, we can get those features out of our calculator. So we're interested in how far apart they are. That is the difference in those two amounts. So we're going to subtract. So for each cell, we subtract the calculated or the expected counts from the observed counts. Now again, we want to be able to add these up, and those differences could be positive or negative. So just like the standard deviation, we need to square each one first to make all the numbers positive. And finally, we want to make it unitless. That is, we don't want it to be talking about people. We just want it to be a number. In this case, it would be people. But when we divide people by people, it becomes a unitless amount. And finally, we add them up. When we do that in this example, we see that chi-squared is the sum. So there's sigma. Sigma is telling us to add up. It's telling us to add up that quotient, because we want it to be unitless, of the squares in the numerator because we want to talk about distances. Distances come from the difference between the observed and the expected. In this data, that gives us a chi-squared of 13.22. Now the next thing that we want to do is figure out our test statistic. That is, we want to get a p-value. So from that chi-squared, we're going to find the area of the right tail of the chi-squared distribution to get the p-value. And like a t-distribution, chi-squared depends on the degrees of freedom. The degrees of freedom here, because there are two sets of categorical variables, is the row count minus 1 times the column count minus 1. So just like for our t-tests, chi-squared is a family of distributions. When the degrees of freedom, df, is relatively small, we can see it shoved up against the y-axis. As the degrees of freedom get larger, we can see it pulled out and kind of squashed and flattened a little bit as well. In this case, when we go to the right from 13.22 with a degree of freedom of 2, we get 0.0013468321. That's less than 5%, which would seem reasonable level of significance for this problem, so we reject the null hypothesis. That means that there is enough evidence to show that class and gender of the survivors of the Titanic are dependent. Here are the two tables side by side, the observed counts, the actual number of survivors in each class and each gender, and then what we observe when we made the assumption from the null hypothesis that the gender and class were independent. So those expected counts came from that. Notice that the totals are the same. Let's take a look at our first example of a chi-square test for independence. So let's bring up the calculator. Let's go into statistics and down to a chi-square test. So 1, 2, 3, it looks like we need 3 rows and 2 columns. So let's name things female and male for our columns, and then first, second, and third for our rows. Now let's put in the information. So 134 female first-class passengers, 59 male first-class passengers, 94 second-class female, 25 second-class male, 80 third-class female, 58 third-class male. Now we've got our chi-squared statistic and we've got our p-value. We can also get the expected count. So notice later we calculate that. So we would have expected 132.0978 and so on. So the expected values are put below. And notice that this is our p-value that we found with the chi-squared test. So here's another example using data we've seen before. This is the data collected off the coast of Ireland of observing dolphins. So here the 2 categorical variables are the time of day, morning, noon, afternoon, and evening, and what those dolphins are up to, traveling, feeding, socializing. The bottom row is a total and the far right column is a total. Remember, when you use the calculator, you won't put in that data. We're asked to test, so we're doing a hypothesis test, whether there is evidence to show that the time and activity are independent. So that will be our null hypothesis. We're also asked to test at a 1% level of significance. So our hypothesis is that the activity and the time period are independent for the dolphins, and the alternative hypothesis is that they are dependent. Our alpha is 0.01. We should say that we were never told whether this sample is random, and for that reason, this may not be a valid test. The expected frequencies are all greater than 5. Go back up and you can see that, oh my gosh, one of them is 0. It looks like feeding in the afternoon is 0. In fact, there are 2 that are below 5. So this assumption is not true, and the results of the hypothesis test may not be valid. So make sure in your assumption you say, we're going to go through with this, we're asked to do it, but the results may not be valid. That's probably the single most important 3 words in this problem. We then use our calculators to find the test statistic and the p-value. Here the test statistic chi-squared is 68.456. That gives us a p-value that is ridiculously close to 0. Our alpha is 0.01, but even 0.01 is bigger than something that's essentially 0. So since the p-value is greater than alpha, we're going to reject the null hypothesis in favor of the alternative. And we can say in words that there is enough evidence to show that the activity and time period are dependent for these dolphins.